Hello everybody, welcome to another video lesson. Today we're looking at vectors now in three-dimensional space. All right, we'll be able to express and operate with vectors in 3D space after this video, so let's go ahead and hop right into it. All right, our vectors in 3D space. You will see them denoted just like this, very similar to our two-dimensional vectors. Now again, we have this third component, however, that is going to be kind of our z component, right? Like we had when we plotted our points in three-dimensional space, right? So in order to graph these, all we're going to do, we're going to plot our initial point and we're going to plot our terminal point. And then we'll just go ahead and connect the two with our vector. Okay, keep in mind when we have three-dimensional vectors, now we have three components, right? We have x, y, and z directions, which means we also have another unit vector, okay? So since our y heads off to the right like this and our x kind of comes out at this angle, now my I, okay, my unit vector in the positive x direction is going to come out this way. My j is going to head this way in the positive y direction. And now we have this unit vector k that's heading up in the positive z direction, right? So keep that in mind that not only do we have three components, x, y, and z, as you can see here with this vector v, okay, we've got our x component in red, our y component in green, and then our z component heading up here in blue. We also have another unit vector, and we can see what these unit vectors look like on the three-dimensional coordinate system. And here are the coordinates for the terminal points of those unit vectors. All right, so we got 1, 0, 0 for I, for j, 0, 1, 0, and for k, 0, 0, 1. All right, so if we don't have a vector with its initial point at the origin, that's okay. That just means that if we had, say, a and b, so we'd have a1, a2, a3, b1, b2, b3, or you might see x1, y1, z1, x2, y2, z2, all right? In order to find this vector in component form, it's the exact same thing as when we had two dimensions, except now we're just going to take one more step here in our z direction. So we'd have b1 minus a1, so we've got the differences in our x's, in our x directions, the differences in our y's, so b2 minus a2, and b3 minus a3, the differences in our z components, okay? And then if we were to find the magnitude of this vector ab, again, we have seen this before, right? We're just taking the differences here and then squaring them, adding them together, and then taking the square root of all of those. But we just add this term for our z components as well. So we got b3 minus a3 quantity squared. Okay, so just this little added step here from our two-dimensional vectors. So if we've got vector a and vector b, and then we have some scalar k, go ahead and write down all of these operations that we can do. We got addition, subtraction, and our scalar multiplication, which, guys, we've really seen before. This is just, again, having this added step here for our z components. That's the only difference that we're working with. All right, so those are our concepts. Let's get into some examples. All right, our three-dimensional vectors, we're going to locate and graph this single vector. I don't know why it says each vector. The single vector in three-dimensional space, and we're given our vector u as a linear combination of I, j, and k. So again, we can think of this in component form, right? So I've got -1, since I just have negative I. Instead of minus 3j, I can think of that as -3. And then for our last component here, we have this +4. All right, so again, we're going to kind of identify all of these separately on each one of their axes, all right? So I've got -1 in our x direction, because again, this is the negative x, this is the negative y, this is the negative z. So I've got -1 in the x direction, I've got -3 in the y direction, and then I've got 4 up here in the z direction. So if I go ahead and kind of plot that out like I would if I were plotting just the point here, okay, so if this was the point, -1, -3, 4, then we just take our vector and draw that with the initial point at the origin and the terminal point at that point that we just found. Okay? Let's go ahead and now let's take the, we're going to find the component form and the magnitude of a vector given the initial and terminal points, and then we're going to find a unit vector in the direction of a b. So we've got our points here. Again, to put this in component form, we just say x2 minus x1, y2 minus y1, z2 minus z1. So here I've got x1, y1, z1, z2, x2, y2, z2, and we just plug those directly. 1 minus -2, 4 minus -5, -2 minus -5. All right, so we simplify that to 1, 9, 3 for our vector AB in component form. Now, if we were to find the magnitude of that, okay, we just take each one of these terms and square them, add them together, take the square root. We've done this before, except without this z term, or this z component. So I've got my A1, A2, A3, plug those in, and the magnitude of AB, this should have magnitude sign right here, is going to be equal to the square root of 91. Now, if we're going to find a unit vector in the direction of AB, that doesn't change with my unit vector equation, okay? Our unit vector for AB is still just 1 over the magnitude of AB times AB, all right? So our magnitude, again, is square root of 91, so 1 over the square root of 91 times AB. If I go ahead and rationalize this, I'll have root 91 over 91, and then multiplying that by our vector AB. Okay, again, this is our scalar, and we're multiplying our vector through. So we just multiply the scalar to each component of our vector, and we'll get the unit vector for AB looking like this. All right, let's do some vector operations then. If we're given W, again, vector Y, and Z, find 3y plus 3z minus 6w. So let's just do this one bit by bit. Okay, so I've got 3y, so that's 3 times our vector y here. So we just distribute that 3 to each component. It's going to look like 9, -18, and 6. 3z, again, I've got our scalar of 3, multiplying that to each component of z. That's going to give us -6, 0, and 15. And 6w, I'm just taking 6 and distributing that to each component. That gives me -6, 24, and -24. So then 3y plus 3z, just doing the first part of this equation here, okay, working from left to right, that's going to be 9 plus -6, and -18 plus 0, and 6 plus 15. That simplifies to 3, -18, 21. And from there, we can take this vector and we can subtract 6w, which we found up here. So that's going to look like 3 minus -6, -18 minus 24, and 21 minus -24. And that's going to give us a final vector of 9, -42, and 45. All right, one last example, looking at some applications here. All right, after takeoff, we got an airplane that is headed east and is climbing at an angle of 18 degrees relative to the horizontal. Its airspeed is 250 miles per hour. If the wind blows from the northeast at 10 miles per hour, find a vector that represents the resultant velocity of the plane relative to the point of takeoff. And we're going to let our unit vector I point east, unit vector J point north, and unit vector K pointing up. All right, so here's kind of our setup here. If unit vector J is pointing north and I is pointing east, then we know that off this way in the negative y direction, that's south, and in the negative x direction, that's west, and up is going to be our z. So here's our plane and the vector when it is taking off. Okay, so we have a magnitude of 250, and this angle to our x-axis, again, this is to the x-axis, is going to be 18 degrees, all right? And then we have wind coming in at 10 miles an hour. It's coming from the northeast, so it's coming from this area here. And it's going to be blowing into the airplane like so. So this, if you can't see, this arrow is pointing off this way. Okay, so we need a vector for the speed of our plane So with this angle here, okay, we need to think of this in each component here. So it's going to be the magnitude of the vector times the cosine of theta. And this theta is going to be our 18 degrees. So right now, I'm just finding this component here in my x direction, component in the x direction. That's what this component is right here. And then 0 in the y. Okay, notice that this thing is it's going up and it's going east. It's not going north or south at all. So that's why I have a 0 here for my y component. Now for my z component, since the airplane is taking off and going up, that's going to be this component right there. Okay, so notice we have our right triangle that we can kind of make up with our horizontal and vertical components. But now this vertical component is actually in the z direction. Okay, it's in the z direction, not the y direction. So that's going to be the magnitude of s times the sine of theta, which again is 18. So that's going to look something like this. Now for our w is the vector of our wind. That's our wind vector. And so again, we're going to have some components here, and that's going to be the magnitude of w times the cosine of theta, and the magnitude of w times the sine of theta. And notice the wind isn't blowing up or down at all. It's just coming kind of parallel with our xy axes. So we know that there is going to be no component for z. That's just going to be 0. It's not going up or down. It's just coming straight across parallel with my xy axis or coordinate plane. Okay, and then it is going in the negative x and negative y directions. Okay, you can see that with the way that we drew this out, because it says it's coming from, the wind blows from the northeast. Okay, from the northeast, so it's heading towards my origin here and kind of in the southwest direction because it's coming from the northeast. So I have a negative x and a negative y component, okay, because of the direction of my vector. And I need to make this assumption here. It didn't give me any relative angle that this was coming in from the northeast. So we're just going to say it's coming in from exactly northeast, which is going to be 45 degrees. So we can go ahead and plug in our magnitudes and our angle for theta of 45. So again, this first component here is that's going to be this component right there. And then our y component here is going to be heading this way. Okay, this is our negative x component here, and this is our y component heading off towards the south direction. Okay, so we can just plug this straight into our calculator. We're going to add these up and find the resultant of our speed and wind vectors. So I've got 250 cosine of 18 minus 10 cosine 45. For our second component, we'll have 0, because we have a 0 here for our s, for our speed vector, minus 10 sine 45. And then we've got 250 sine 18 plus 0, because again, our wind has a 0 for the z component. It's not going up or down at all. So we can plug those into a calculator, and we're going to write this as a linear combination of I, J, and K, which will look just like this. All right, guys, that is all that I have for you today. Good luck with your practice.